The Higgs boson, unveiling the God particle. Introduction. Hello and welcome back to CHIZHIM Science Tech YouTube channel. Today, we're diving into one of the most mysterious and revolutionary discoveries in modern physics, the Higgs boson, popularly dubbed the God particle. You may have heard about it back in 2012 when headlines around the world exploded with the phrase, "Scientists discover the God particle." But what exactly is this elusive particle? Why was its discovery so important? And what does it mean for the future of science and our understanding of the universe? Grab your thinking caps, because we're about to embark on an exciting journey into the fabric of reality itself. Phase 1. What is the Higgs boson? The Higgs boson is a fundamental particle associated with the Higgs field, an invisible field believed to exist throughout the entire universe. It's not a particle like a proton or electron that makes up atoms. Instead, it's a quantum excitation of this field, kind of like a ripple in a cosmic ocean. Think of the Higgs field as a vast, invisible energy field that permeates everything. Stars, planets, you, me, everything passes through it. The Higgs boson is the messenger of this field, the proof that it exists. And here's the kicker: this field is the reason particles have mass. Without it, everything in the universe would zip around at the speed of light, incapable of forming atoms, molecules, or life. Phase 2. The mystery of mass. For decades, physicists wondered, why do particles have mass? Why is a proton heavier than an electron? Why do some particles like photons, light particles, have no mass at all? The answer lay in the Higgs mechanism, proposed by physicist Peter Higgs and others in 1964. The idea is this: as particles move through the Higgs field, they interact with it. The stronger the interaction, the more mass the particle gets. It's like walking through a crowd. The more people grab at you, the slower you move. That drag is like mass. So the Higgs field doesn't give mass, it resists motion, and that resistance is what we interpret as mass. Phase 3. The standard model of particle physics. To truly grasp the importance of the Higgs boson, we need to understand the standard model, the reigning theory that explains how all particles and forces, except gravity, interact. It includes 12 fundamental particles like quarks and leptons, 4 fundamental forces: electromagnetic, strong, weak, and gravitational, though gravity isn't yet fully explained by this model. Force carrier particles like photons and gluons. But there was a big hole in this model, a missing piece, explaining how particles get their mass. That missing piece was the Higgs boson. Without it, the standard model falls apart. Phase 4. The Higgs mechanism, how it works. Imagine the Higgs field like a room full of paparazzi. When a celebrity walks in, everyone crowds around, slowing them down. That's a metaphor for mass. A less famous person gets less attention, less interaction, less mass. A photon walks in, no one cares, it's massless. The Higgs boson is the particle associated with this field. Discovering it was like proving the paparazzi crowd actually exists. In physics terms, this interaction mechanism gives rise to what we measure as inertial mass. Without it, particles wouldn't clump together, and the universe would be a glowing soup of massless energy. Phase 5. The search begins, why it took decades. Even though the theory was proposed in 1964, the Higgs boson wasn't discovered until 2012. Why? Because it's incredibly difficult to detect. It's unstable, extremely short-lived, and can only be created in high-energy collisions, like those simulated in particle accelerators. Enter the Large Hadron Collider, LHC, the most powerful machine humans have ever built. Phase 6. Building the Large Hadron Collider. Located near Geneva, Switzerland, the LHC is a 27-kilometer ring buried underground. It accelerates protons to near-light speeds and smashes them together, recreating the conditions just after the Big Bang. Scientists at CERN, European Organization for Nuclear Research, used this collider to probe deeper than ever into the subatomic world. 2 major experiments, ATLAS and CMS, were built to detect the Higgs boson, among other goals. Years of preparation. Billions of euros. Thousands of scientists. All for a chance to glimpse the elusive God particle. Phase 7. The discovery of the Higgs boson, 2012. On July 4, 2012, the world of physics changed forever. Both the Atlas and CMS experiments independently announced they had found a new particle consistent with the Higgs boson, at a mass of about 125 GeV, giga electron volts. It wasn't just a particle, it was the final missing piece of the Standard Model puzzle. Peter Higgs himself was there, visibly moved. He later received the Nobel Prize in Physics in 2013, along with François Englert. Phase 8. WHY it's called the God particle. The nickname God particle came from a book by physicist Leon Lederman, who originally wanted to call it the Goddamn particle, out of frustration at how hard it was to detect. Publishers, sensing a marketing opportunity, shortened it. Though controversial in scientific circles, the name stuck. But let's be clear, the Higgs boson has nothing to do with theology, it's a cornerstone of quantum physics, not religion. Phase 9. The aftermath, confirming the model. The discovery led to a new era in particle physics. It validated decades of theoretical work and confirmed that the Higgs mechanism is real. But it also raised new questions. Why does the Higgs field have the value it does? Why is the Higgs boson so light? Could there be more than one Higgs boson? Is this just part of a larger theory, like supersymmetry or string theory? The Higgs wasn't the end. It was the beginning of new mysteries. Phase 10. The Higgs field and cosmic evolution. The Higgs field likely played a major role during the early moments after the Big Bang, potentially influencing how particles formed and how the universe expanded. Some theories even suggest the Higgs field could connect to dark energy, inflation, or multiverse models. In short, understanding this one particle might help unlock the ultimate secrets of the universe. Phase 11. The future, beyond the Higgs. Scientists are now planning next-generation colliders, even larger and more powerful than the LHC, to study the Higgs boson in more detail. Goals include detecting rare Higgs decay modes, investigating potential Higgs siblings, searching for connections to dark matter. We've found the particle. Now, we want to know everything about it. 12. Conclusion: a particle that changed physics forever. The discovery of the Higgs boson is one of humanity's greatest scientific achievements. It confirmed our understanding of the subatomic world and opened doors to new realms of physics we never imagined. As we continue to explore the universe, one thing is clear: the smallest things can lead to the biggest revelations. Thanks for watching CHIZHIM Science Tech YouTube channel. If you enjoyed this deep dive into the Higgs boson and want more mind-blowing content like this, don't forget to like, share, and subscribe to CHIZHIM Science Tech. Turn on notifications so you never miss a journey into the universe's greatest mysteries. Until next time, stay curious and keep exploring.